All right, 4.4, linear programming. It says linear programming is a method of finding a max or a min value of a function that satisfies a given set of conditions called constraints. So these constraints here, they're conditions that have to be met, like something has to be less than or greater than something. And they're one of the inequalities in the programming problem. The solution to the set is basically when we graph all of these inequalities and we shade it, it's that overlap region, or in this case, it's known as the feasible region. So this is the overlap area. So it's kind of just an application of what we did in 4.3. So let's graph a region. Let's look at a real life problem. So this problem kind of was inspired by, if you take a peek at this website right here, talking about green roofs. And there's a lot of attention now with buildings, putting greenery on top of them in big cities. And there's benefits, reducing urban heat, rainwater management, rainwater purification. Today, the example is focusing on CO2 reduction because plants absorb CO2. They take that out of the air. So that's kind of what we're going to be looking at in this example. So Mackenzie is planning a green roof that will cover up to 600 square feet. So that's going to come into play. This is one of our constraints. We only have 600 square feet on top of the roof. Two types of plants. We have a blue lagoon sedum and a raspberry red sedum. The blue one covers 1.5 square feet. So that's how much area it takes up. And then the red one covers 2 feet, so 2 different size plants. Both plants cost $250, so there's not a difference there. And the project's got to be less than $1,000. So we need to write the constraints and graph the region. So first let's define our variables. Normally I would use blue, B, and R for blue and red, but because we're going to do this in Desmos, I'm going to use X's and Y's. So I'm going to let X equal the number of red plants, and I'm going to let Y equal the number of, let's change that because I think it came first. We're going to do X equals the number of blue, and Y is going to equal the number of red. There, maybe that'll help us keep this thing straight. Here we go. So now we got to write our constraints. Well, there was no limit on the number of plants. All right. So the number of blue plants is greater than or equal to 0. The number of red plants can be greater than or equal to 0. So there was no plant count. The square footage was, we had to be less than or equal to 600. So we need to be less than or equal to 600 square feet. Well, the square footage was, a blue was 1.2. So 1.2 square foot times every blue plus 2 square feet for every Y. So there's our square footage equation. Now we have the money equation. And the money equation said that the plants cost $2.50 each. So we have $2.50 times the blue plant plus 250 cents times each of the red plants, and we need to keep it less than $1,000. Now, we could do this system by hand. It'd take a little while. I'd have to solve them for Y, put them in slope-intercept form. But for these problems in 4.4, we're going to use Desmos. So I'm going to jump over here to Desmos right now, and we're going to pop these in. So let's come over here and open up Desmos, and let's just enter them in. So we need X. I'll go to my little keyboard down here. X is greater than or equal to 0. It's shading it for me. Y is greater than or equal to 0. Let's kind of get here. should be in the first quadrant because we're talking about positive number of plants. So let's kind of zoom out. Don't know how many plants we're going to have yet, but then we had 1.2 was the x plus 2y had to be less than or equal to $600. So now we got an overlap of this triangle right here. And then we have another one. We have 2.5x plus 2.5y. And that's going to be less than $1,000. Ooh, that purple kind of took over everything. So basically, it looks like we have this kind of trapezoid looking thing. So we could translate these points on our graph. I'm going to just kind of focus in and see if maybe I can change some colors here, although I don't know how much it's going to help it. Looks like it's not going to help it very much. What's this number do? Oh, it makes it a little bit lighter. Maybe that's kind of make it a little bit easier to see. Either way, it's this area right here. We're trapped between 300 and 400. And then we have this weird spot where these lines cross at 250, 150. All right, so 300, 400, 250, 150. So let's go back to our sheet, see if we can put this on the graph. I'm just going to put the region that actually matters. So this was the region 300, 400, and 250, and 150, which is right about there. So if I was going to kind of sketch this thing out roughly, we're bounded on all sides. We have boundaries all the way around. But really, anything in here is fair game. So remember, X is the blue plants. And then our y-axis is the red plants. So any combination in there can work. What I want to focus on now, and this is what I'm getting ready to teach you here in a second, is that these boundary points, so this 0, 300, and this 250, 150, and this 400, 0, and 0, 0, which isn't really very interesting in this example because there'd be no plants. Those four vertices are the most important part of this feasible region. So we're going to go over to the next little bit in the bottom, and we'll kind of talk about a principle here, and then we're going to use these numbers for the next part of the question. So we scroll down. It says, in most linear programming problems, you don't want to just graph the feasible region. Usually you're trying to minimize or maximize a certain function, and this function is called the objective function. So that's kind of a word there that you need to kind of know what it means. So the objective function. And the objective function either has a minimum or a maximum, or neither, or both, depending on what we're doing. Your regions could either be bounded or unbounded. So notice in our example, it was very similar to this. We had a bounded region, which means we can have a max, we could have a highest point, or we could have a lowest point. If it's unbounded, so looking at these two examples on the right, notice there's no bound here on the bottom, so we only have a maximum. This one, there's no bound on the top, so we only have, a minimum, but we're not going to have both. And then the most important part is right down here, and it says, if an objective function has a max or a min, it must occur at one or more of the vertices. So the vertices are key. Those points are key. And then it says, there's more advanced mathematics where we could prove that. But right now, you're just going to trust me that that's where it happens. So let's go down here and let's figure out what our objective function is going to be. Well, this kind of ties into that website I showed you earlier. This time we're trying to help control air pollution, and we're going to focus on, we want to maximize carbon dioxide. So that's our objective. We want to maximize carbon dioxide. Well, we need an equation. And we have some numbers over here. It said that the blue plants absorb 1.4 pounds of CO2 per year. And the red one does 2 pounds, or actually 2.1 pounds of CO2 per year. So the red plants tend to absorb a little bit more. So we want to maximize that function. So let's write our function. The carbon function is, I'm going to do 1.4 times all the number of blue plants plus 2.1 times the number of Y plants. And that's the function we're trying to maximize here. Now, when we did our vertices, let's kind of go through here and let's look at our table that we had. We had 0, 0 was somewhere in the mix. Jumping the gun a little bit. 0, 0 was 1. We had 0, 300 was another. We had 250 and 150. And that would be 250. Remember, these are the blue and these are the red. So these are combinations. And then the last one was 400 blue and no red. All right. One of those is going to maximize the carbon dioxide absorption. So what we're going to have to do, we're going to have to plug these values in. Well, this first one, if I plug 0 in, I get 0. So I know that's not going to be a solution. But what if we put all red plants, 300 red plants? You know, it seems like it'd be a good idea because it does do the most. It's a little bit bigger in size, so we could only fit 300. But let's check it out. So if I do 1.4 times no blues plus 2.1 times all the reds, we're going to get a grand total 630 pounds of CO2 per year. So a pretty big number. Now let's see if we do a combination of both. If we do a 250, 150, 1.4 times 250 plus 2.1 times 150, and that shook out to be 665, so that's even better. Now what if we did 400? So this is a lot of plants, 400 plants. So 1.4 times 400 plus 2.1 times 0. And that comes out to be 560. So it looks like our best solution is right here. So we want to have 250 of the blue plants, and we want to have 150 of the red plants. So it's kind of a systematic way of looking at all the constraints, getting the feasibility region, finding your vertices, and then plugging your vertices into the objective equation to see when there's a maximum. Some problems we may want to minimize something, but this one was a maximum. All right, number 3, this is just going to help us get a little bit more practice with the process. There's really no story problem here. I don't even know what the objective function represents, but we do have our 4 constraints. We do have the objective function. So let's go ahead and let's graph this. And for this problem, I'm going to graph on Desmos so that we can get those vertices and we can get that shaded area. So let's try this. Pull it back up, cancel all these guys out. And here we go. So we had, and maybe I'll try to, what if I slid this over, kind of slide this over. so that we can still kind of see our equations. That might be kind of helpful. All right, so we want x is greater than or equal to 0. And it looks like I gotta go up a little bit. X is greater than or equal to 0. Then we want y is greater than or equal to 1.5. Then we want 2.5x plus 5y. This will be a little easier for you if you're looking at a paper and then you have your Chromebook. You're not trying to split the screen like I am up here. And then the last one is this 3x plus 2y less than or equal to 12. All right, well, my zoom is so far out because of those plants that I can't see what's going on. So we got to go in, go in, go in, go in, go in. It looks like the region that's trapped is right here. We have that point at 0, 4. I'm going to write these down on a sheet of paper, 0, 4. Then we have this point at 0, 1.5. Then we have this point, which is at 3, 1.5. Then we have that intersection, which is at 2, 3. All right, so we have our four points. So now I'm kind of done with this. Get it out of the way. And let's bring you back over. Boom. All right, let's see if we can get a decent looking graph of this and wrap up this last example. So I'm not going to do all the lines here, but I am going to do the feasibility region and then the vertices. So we have one at 0, 4. We have 0, 1.5, 3, 1.5, and 2, 3. All right, so there was our feasibility region. And we know that we need to test our vertices. So let's test the 4 points. 0, 4, 0, 1.5, 3, 1.5, 2, 3. And our equation is P equals 25x plus 30y. So let's start plugging some numbers in. So 25 times 0 plus 30 times 4, that's going to be 120. If I put 0 in for x, that's 0. 30 times 1.5, that's 45. 3 in there, that's 75 plus 45, which is another 120. Tie going on. Put a 2 and a 3 in, we get 50 plus 90. Finally got a winner, 140. So it looks like when x equals 2 and y equals 3, we have a maximum. We've maximized it. Now, if this word would have changed, it would have said minimize, then this would have been the right answer. So it all depends on the wording of the question. Hopefully that helps you out, and be sure to have your Chromebook going so you can actually graph these on Desmos. It would be a lot easier than trying to put all this on a graphing calculator. See you.